This question is about the reaction of alkanes. Alkanes can be used as fuels. Give an equation for the combustion of heptane in an excess of oxygen. So excess means it's going to be complete combustion. So C7H16 plus O2 is going to give carbon dioxide and water. So we balance this using macho, so there's no metal, there's no any other element, so it's just CHO. So start with the carbons, 7 on the left, which means I need 7 on the right. Hydrogens, I've got 16 on the left, which means I need 8 lots of 2 hydrogens that I get in water. And then 2 7s are 14, plus 8 is 22, which means I need 11 lots of 2 oxygens. Always a good idea to put the state symbols in. If they are required, then obviously they're there and you need to get them right. But if they're not required, it doesn't matter if you get them wrong. So this is likely to be a liquid. That's a gas. That's a gas. And under normal combustion, that would be a gas. But if it said the standard enthalpy change of combustion, that would be a liquid. Okay, part B. Heptane can be obtained from catalytic cracking of C6H34 at a high temperature. So identify a suitable catalyst. So zeolite is the standard catalyst that we use. Give one condition other than high temperature. So moderate pressure. And so give an equation for the catalytic cracking of 1 mole of hexadecane, so C16H34, so that is cracked into, to produce 1 mole of heptane, so C7, so H2N plus 2, so that's 2 7s are 14, 15, 16, plus 1 mole of cyclohexane, so that will be C6H14, but you'd need to take 2 hydrogens off, one for each carbon where it joins to become cyclic. So that's going to be C6H12. And then one other product is going to be the difference between this side and what we've got so far all together here. So 16 carbons, take away 7 carbons, take away 6 carbons, leaves you with 3 carbons. 34 hydrogens, take away 16 hydrogens, take away 12 hydrogens, leaves you with 6 hydrogens. Alkanes can be used in free radical substitution reactions to produce halogenoalkanes. Give the equation for the propagation steps in the reaction of butane to form 2-chlorobutane. Okay, so never use molecular formulas here. So butane is CH3, CH2, CH2, CH3. Now that will be cracked with the free radical, which will be chlorine. So that's going to make HCl because it rips a hydrogen off. Now the key thing here is you're making 2-chlorobutane, which means the radical is going to form on the second carbon in the chain. So CH3, CH, that's where the hydrogen has been ripped off because we're going to make 2-chlorobutane, CH2, CH3. Okay, the second step, so we start with the free radical that has formed, so CH3, CH, radical, CH2, CH3, plus chlorine that didn't undergo homolytic fission, and then CH3, CH, that's where the chlorine is going to go, CH2, CH3, and then that regenerates the chlorine free radical. So at the start of this, if you remember, I said not to use molecular formulas because C4H10, if you started with that, over here you would C4H9 and the dot would be on the carbon, but it's ambiguous. You're not actually stating which carbon the free radical is in, and because we're making 2-chlorobutane. It's a good habit to be in anyway. Do not write them as molecular formulas. Always do them as structural formulas. Always put the dot on the carbon with where the chlorine is going to join. Okay. D. So chlorofluorocarbons are a group of halogenoalkanes currently banned in many countries. They can't be used as solvents or refrigerants because their effect on the environment. There's the structure of one there. Identify the radical, chlorine, that is responsible. Explain with the aid of equations why a single radical can cause the decomposition of many ozones. So we need the ozone depletion propagation steps. So ClO dot, and the dot is on the oxygen there, plus O2, and then the ClO dot radical reacts with another molecule of O3 to give the chlorine radical back, and O2. Of course, this one radical is regenerated. So we're just going to put a statement here that the chlorine free radical is regenerated.